Okay, good. So today's lesson probably we're going to take you straight 2 hours, so bear with me, lah, yeah. Now, surface water sampling is probably one of the biggest component in sampling, and I will going to like repeat a few points that I have given to you earlier during my first lecture on the introduction of the sampling. Okay. So for today, we're going to discuss specifically surface water sampling. So lecture, we're going to go through the fundamentals first, the principles, the planning, and also the techniques. Now, I probably will not go into detail of a few things simply because you must have learned it in analytical chemistry subject. So I don't see the point of repeating it. Rather, today's lesson we're going to be specifically on sampling, water sampling. So the lecture content, we're going to probably have like pre-lecture movie, but I think I'll skip that and let you watch it. Because in this lecture movie, most of the content is displaying the techniques. So, I mean, at the end of this lecture, we're going to go through the techniques in lecture, but you can always come back and look at the actual video, lah, yeah. Now,
Actual video lah ya.
okay, so I need other people to switch off your microphone if you're not speaking, and let me give the lecture. Okay, thank you. Okay, next point is sampling strategies of the water pollutants, practical approaches. So in the water sampling, we also have some rules to follow. All for the sake of the accuracy and also to minimize the source of error. So there are strategies that we need to follow. Later on, I will evaluate. I will explain to you the details. Okay. Number three, water sampling equipment and devices. So these are the simplest and the most basic things that you're probably going to use and bring to the field when you want to conduct water samplings. Probably not everything, but I'm going to involve the most usual things that people bring. Okay, number four, field measurements. Now, apart from bringing samples home, like last time when Mr. Faris asked you question, would you like to take samples home or you want to analyze straight away, measure it, the parameters straight away on site? The answer is definitely measure on site if you can, because you remove the possibility of error due to transportation. So a few things that water can do in terms of field measurements, and definitely we can do that. And the details is probably we're going to talk about field quality control, quality assurance samples. So these are the techniques that I suspect you might have learned it in analytical chemistry. So we're going to repeat a few. First, a
Buat
few.
balik oh.
If you forgot, I think I need to go out for a while and make sure everybody is actually muted. Apparently, somebody is not muted yet. Okay, so everybody is muted. Can you still hear me?
Yes.
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 So
Yes.
now I can ensure that nobody is talking right now. Okay, now last point, pre-treatment extraction technique. Now this one I was supposed to tell you the details, but I think at the end of this lecture, at point number 5, I think probably what you're thinking, probably you want to get out of this lecture as soon as possible. Okay, I won't stop you because why? When a treatment and extraction technique, that actually is part of the analytical chemistry part, which I think probably is not so applicable for sampling, which is this subject. So I'm going to let you know that this section exists and is very important. Only if you request and you want to ask question regarding this part, then only I will answer. Okay, so today's lesson is purely sampling technique, the management, and the quality control. So these are the two lectures that I hope you can go in and watch later, because for time's constraint, we only have 2 hours today, so we need to finish it on time. Okay. Now, to begin with, I'm going to discuss with you the strategies on how to conduct sampling of surface water. Now, the strategies here depends on what pollutants that you're dealing. Now that is why at the beginning of this lecture, of this course, I given you an overview before you even conduct it is important for you to plan, because once you have planned, you have an idea what you're dealing, and then you can prepare accordingly. And as required by water sampling, you will need to see what pollutants that are involved or contaminating the site, or what medium that you are dealing with. In this case, is water. Then you have to prepare and have strategies accordingly. Because mind you, when you have several pollutants, then things gets a bit messy, or I would call it more challenging. Because why? You will have to rank and identify these pollutants, and then you will have to understand what's their behavior, because no pollutants are going to have the same properties. Some of these pollutants, they might just stay put, they're not going anywhere, like for example heavy metal. But in pollutants, we also have organic pollutants that sometimes very soluble, sometimes very not soluble in water, but they stick so strongly to the soil particles, but yet they are also volatile. So do you see what I mean here? I'm talking about the oil contaminants. They are very sticky to the soil, not so soluble in water. They float on water, but when the temperature gets hot, they also volatilize. So these are the things that you need to give consideration. Uh, I think probably some of you might got worried lah. How then what to do? There are so many pollutants, kan? So we're going to learn things one at a time lah. So don't worry. We're going to take you through a few things. So for the sake of you answering question in test and examination, the number of pollutants is not going to be that many. So relax lah. You can relax. You're probably going to see questions that address only one or two pollutants, maximum lah 3 to 4. I mean, even with 3 to 4 also, I mean, the question will be probably involved in essay question. So, yeah, it's hard, but it's part of the syllabus, yeah. Cool. So we're going to go through the details of strategy now. So first thing first, know your problem. First of all, what is the problem that you need to solve? And from the problem, you will need to determine the objective. Now, there are like 4 strategies right here that you need to consider here. What exactly that you're going to do? What exactly that you're going to achieve? What do you want to achieve, possibly? Okay. So this slide actually is taken from USGS, United States Geological Survey. So this department is under United States that analyze and monitor, not analyze, they monitor the water quality and also soil quality uh, from underground water, and also the contamination, because this unit in United States deals specifically with mining activities. So whatever the mining activities, they will get involved. In Malaysia, there's an equivalent department. It's called Jabatan Mineral dan Galian. They are the same. So in Malaysia, we have equally the same thing. And Jabatan Mineral Galian actually is very active now in Pahang and also in Perak, because there are still mining activities over there. Now, what do they do? Now, in here, they have 4 types of sampling that they possibly want to do. And these 4 reflects what exactly is their monitoring objective. Okay, number 1, chronic standard. So the point here says sample at equal time interval to obtain is 4 days mean. So in this standard, is like they will want to like measure how bad is the level of pollution. Another similar standard is acute standard. Now in this case, the chronic standard and acute standard, I think probably the term itself you can differentiate. What's the difference? Acute means very highly contaminated. Now in this case, you can see like the interval or the timing that they take the sample. Some is like probably more relaxed, longer time frame, whereas for the acute one, the most, I mean, you can say lah, the situation where it is very contaminated, okay, the soil or the groundwater, they can like they can have like a frequent interval in daily basis. So it depends on the level of pollution. If the level of pollution is like very low, very ambient, low level, then possibly you don't have to be so frequent. If it is very highly contaminated and it changes very quickly, then possibly you want to have as frequent sampling as possible. Now, to tell you the truth, lah, if there is an acute standards that they need to follow and they are monitoring a very quickly changing and highly contaminated level of the pollutants, usually they don't do sampling anymore lah. I'm talking about the situation when we have in Pasir Gudang. Last time Pasir Gudang, they were like so acute that some schools in Pasir Gudang, the students actually fall ill. So that is considered acute already. So what was happening then? There were no sampling. People go straight there, bring in their monitors and monitor straight away because they want to find where is the source. So that's an example of these two. Now the other two is temporal or spatial analysis. Temporal means depends on time. So based on time change for for a duration of maybe 1 week or maybe 1 month, they want to observe how is the change. Now this change, surprisingly, some people also observe in 24 hours because why? In 24 hours, how many hours of daylight? Maybe 12 hours of daylight. In this daylight, the temperature also rises up, and after that, it goes down. Now, perhaps you don't realize the temperature change or difference in Malaysia because, after all, we are tropical countries. Tropical countries, I mean, the hottest temperature will be around 40 degrees Celsius, and then the coldest is 25. But if you're going to a temperate country, or maybe in desert area, their day temperature could exceed 45, 50, nearer to 50 degrees Celsius daytime, and then at night time it can fall down to around 10 degrees Celsius. That can be the difference in temperature, and because of difference in temperature, the behavior of pollutants also might change accordingly. So that's why it may warrant a 24-hour sampling if that is the case. Yeah. However, in Malaysia, I don't think so. I don't think we ever have this one, unless there is an acute standard here. Yeah, because it changed so fast, so you have to monitor every hour or maybe every 2 hours. Uh, again, again, if you refer to the events in Pasir Gudang, they also don't monitor every hour. They also monitor daily because why? Once you take the sample and want to analyze, it takes days, to come up with the result. The same goes to a few years ago when Malaysia was having that haze episode. That also, the result comes in like every day in daily basis, not in hourly basis. No, I mean, so far, like, as far as I know, no equipments can actually give you the monitoring in hourly basis, except that you have like real-time monitoring. Yeah, that can be said. And then lastly, comparison of load, temporal or spatial. Oh, just now I forgot. Spatial analysis is the objective of this monitoring plan is to see how far the pollutants has spreaded. So that is the difference between temporal and spatial analysis. So these are the examples of the monitoring plan that possibly can come up. And what is the point here? Now the point here is that due to this different variation, they change. They change with time. They change with space, and they even change with the environmental elements like temperature or maybe what do you say? The rainfall, perhaps precipitation. That also might change the dynamics of the pollutants in the environment. And usually sampling plan have to be very mindful on those factors and factor in what are the things that you need to consider. There are so many variables, they vary so much. Least that you can do is understand the changes. Okay, like what you can see right here, aqueous metal concentration are highly variable. Because why? Because when we say aqueous, that means these metals are dissolved in liquid rainwater most likely. And then what? They move everywhere, right? They can move along the surface of the earth as surface runoff, or they can seep into the earth and go down. And then when it goes into the soil, it can go anywhere in the direction, as we've learned in soil science and analysis. So these are the things that might going to affect the dynamics of these metals in aqueous phase in water. So location of the catchment, because they also look at where does the direction of the water surface flow. Not only that, they also looks at the lithology. Lithology actually sees what is the properties, physical nature of the earth because some earth they are not so porous. So if they're not porous, then they flow along the surface. But if they're porous, then they flow through. So a lot of factors that can affect that. And also they look at climate, temperature, and also how heavy is the rainfall, how heavy is the precipitation. That also might going to see, because why? If you have a very high rainfall, dilution may comes in. So the metals that you analyze is probably does not reflect the actual concentration due to the dilution due to high rainfall. That also might factor in. Okay? And also geochemical process, because we also know that the minerals or the organic compounds on the surface, they might not going to like stay so inert. Reactions happens all the time, and it depends on so many factors. Yeah. But you can actually now next time, I know you're in the process of planning with your sampling plan, but usually like in sampling plan, the number one thing that you should remember and be mindful is season. No matter what, no matter where you are, seasons comes in. Temperate countries, there are 4 seasons. Malaysia, how many seasons? You can say 2 seasons, wet and dry season. Monsoon, they call it. So these are the things that you need to consider first. What time do you go in and do your sampling? Are you going in during dry season or wet season? And the big question is why? If you want to go into wet season, doesn't mean that you're wrong, but you have to justify lah why you want to go into wet season and why dry season. Now, most of the time lah, as a researcher myself, I usually don't want to answer that question, and usually I just go in on both seasons just to see lah. I mean, just to see in wet season how is the level of pollution, and dry season, so that we reason and be representative of the level of pollution in the environment throughout the year, and no need to answer lah why wet season dry season, because there's no right or wrong answer, both also correct. You just have to answer why. Yeah. And then stream flow. Now, as affected by seasons, sometimes there are like very high precipitation, high rainfall, like what we are about to experience right now. We were in dry season just a few weeks ago, and suddenly it has changed. So you can see that almost every afternoon it rains. Even it rained just now, kan? Um, if it rains, water has to go somewhere, and to go to the river, to the channels, and then to the sea. So the storm water also might be factored in, because why? Um, at times during dry season, the flow possibly is not that high, but in wet season, the flow might be higher, so the volume is higher. Whatever that you sample during wet season is definitely not the same during dry season. Like I said to you earlier, the dilution factor might factor in. Apart from that, the flow also might factor in. Because when you have higher flow, what happened to the dynamics of the metal? That might also change. Yeah. And also daily basis. I think in daily variation, I think it's best that I show you the next slide lah. Yeah. So this slide shows you the changes of several metals. I won't call it heavy metals first, because one of it is not metal. But you can see the variation over 24 hours. Is it 24 hours? No, not 24 hours. I think 48 hours, if not mistaken. And you can see now these are like in the x-axis, these are just time frame in terms of hours, and also the concentration. Can you imagine in heavy metals also, you can see in liquid form, the changes can be that significant, especially when you look at zinc. They changes a lot. What makes those changes so significant? It's actually the cycle, nighttime and daytime. Like I told you earlier, during daytime you have sunlight. Sunlight what? Brings higher temperature. Temperature is just what? Because if you look at these metals, some of them, they are possibly exposed to sunlight. And mind you, sunlight also may encourage oxidation. They call it photooxidation. So these are the things that you need to be mindful. But once you know the heavy metals that you are dealing with, then you possibly have a better idea. Let's say if your sampling is conducted very early in the morning, maybe if you look at here, 6 o'clock. 6 o'clock in USA is already like very bright, not like in Malaysia. 6 o'clock is very bright. So you can see like most of the heavy metals, they are very stable. At least these are what is so-called the baseline. Okay. These are the state where the changes can be said at the minimal. But if you're sampling, if you take your water sample after 12 o'clock, you're going to see a sudden dip. Arsenic remains the same, but the others suddenly dip very low. Does that represent the level of concentration or level of pollution that you are supposed to analyze? Maybe yes, maybe no. Because, like I told you, there's no right or wrong. It's just like whether the sample represent the conditions that you want to sample, and does it answer your objective. I don't know. Maybe the monitoring plan specifically say they want to find out the metal concentration afternoon. So afternoon, yeah, very low. But in the morning time, maybe very high. So it all depends. It all depends on what is your objective. And then once you know what you want, then you come back to your pollutants. What pollutants that you have, and how do they change? How do they change according to the conditions and also environmental parameters? Yeah. Okay, I think we're going to continue and finish up this part. So like I said, the flow, the higher the flow, the lower the concentration because due to dilution factor, and then temporal sampling scales. Different times, like I said, may be subjected to different seasons, and also these are the factors that I've already explained to you earlier. So I'm just going to, yeah, coming to this slide, I'm going to stop for a while, and I'm going to ask you, is there any questions so far regarding the variations that might happen? Still early in the lecture, actually. Any questions so far?
No.
So everybody can understand, okay? By the way, I don't expect you to have questions because it's early. Now, I think probably from this point onwards, things are going to be getting more interesting because these are the one that will come up in your exam. I can tell you straight away right now, okay? Because these are the things that you need to give consideration. It's sort of like, why I say it right now that this is a question, because from this point onwards, it needs you to give your own opinion. Let's say if you're facing one condition, what sample that you want to take first in order to analyze as such and such contaminants. So these are a perfect material, I would say, perfect material for me to make because you cannot get the answer from the internet. Search whatever you want. You cannot get the answer from the internet. You have to use your own mind and give me the answer. So I can tell you straight away, this will be one question. No question about it, yeah? Okay, sequence of sampling matrices. Now, in this slide onwards, we're going to learn what are the things that we need to sample first, what are the things that we need to sample later, in a way that we're going to minimize interference or contamination. Now, in sampling, you cannot run away from sampling other matrices. You possibly sample air. Okay, air does not mix with water and soil, so no problem. However, most of the time, you're going to have trouble going to sample between water and soil because if you sample from the same location, the contamination might going to happen more so from soil to water phase. So these are the things that you need to be mindful lah, yeah. So according to this, what matrices that you should start sample first is you should start from the least contaminated sampling location to the most contaminated. The strategy is very straightforward and obvious lah, because if you start from the most contaminated, then everything will be contaminated. So you only get one sample lah. Good. Okay. So the strategy is, first of all, you collect the water. No matter where you go, stream or maybe riverside, lakeside or ocean, you collect the water first and do not disturb the sediment. Yeah. So collect the water, maybe upper strata of the lake or maybe upper strata of the river. And in fact, most of the time when you want to collect stream water, you only collect from the top, not from the bottom, because if you collect from the bottom, you're also collecting the sediment and also some of the things that not supposed to be part of the water. Well, it is, but at the bottom part. So once you collected water, then after that what? You proceed to a deeper interval. So the deeper you go, the more sediments it will contain. Kan? Until you reaches at the bottom, at the river banks, for example, then that is pure sediment. Okay? So the point is very simple. Start with water and you end with sediment or maybe soil. Or if you're collecting just plain water sample, you start from the shallow part first. Yeah. Start from the surface. Start from the shallow part, the upper part of the river, and then you proceed to the deeper region, which is probably containing more sediment. And then the final point, if you're going to sample shallow stream, I think this is mostly your case, like surface runoff, for example, it's already very, very thin, not very deep. Uh, so you have to consider where is the direction of the flow, because you will need to start from downstream and then you have to work upstream. Downstream means all the water will flow to that direction. So most of the time when you start from downstream, whatever water that you collected for sure is going to be clean. However, if you work the other way around, if you go to upstream, you go to high ground and you start sampling from there, whatever water from downstream is going to fill with all the sediments. You know why? Because when you step into the river, you catch out the sediments at the river bank, then everything flows up, finish lah downstream. So that's why you always start from downstream, then you go up. Yeah. Okay, so far can understand kan? Very straightforward though. Straightforward. Okay. Okay, so if that is the case, then yeah, that was simple. But I think this one possibly, if you're not good in chemistry lah, yeah. Okay, now the next part of the sampling sequence is based on the analyte, or in other words, the contaminant. If you can see from number 1 to number 6, they are all contaminants, but they are all very different in nature. Because if you look at number 1 and number 2, these are organic contaminants. Why they are located on top? By the way, do you know what is VOC? Do you know what is VOC?
Volatile organic compound.
Okay, very good. Volatile. The name itself tells you it's volatile. That means you can see it possibly absorbed in the liquid phase or solid phase, but they have a very high tendency of evaporating with high temperature. So in this case, you can say that the challenge of handling these contaminants is that they escape very quickly. And if they escape very quickly, they will disappear. They might be disappearing. They're having a tendency of not staying too long. And we have a different strategy on how to handle this compound. The next one is, very much the same, semi-volatile. Now, this is possibly, you can imagine as something that is oil phase that can be volatile, but most of the time they're going to stick to the solid surface like soil or sediment particles. But either way, they also can be volatilized if the condition is right. Now, from number 3 and number 4, number 3 and number 6 onwards, these are the ones that uh, are more stabilized. Most likely they won't going to volatilize, but they might be dissolved. They might be dissolved according to certain condition. Or if they don't dissolve, they just exist as like a inorganic solid phase. So they're either soluble or they're not. But the thing is that depending on what objective that you want, yeah, because when we want to in environment management, most likely total metal is not some parameters that will accurately reflect the risk factor. Do you know why? Do you know why total? Okay, by the way, first of all, do you know what is total metal? Total metal. Do you know what is that? Yes or no?
No.
No.
Okay, most of you, I assume most of you don't know. Okay, now total metal by definition is every single metal that is contained in your sample, either soil or liquid sample. Now air, I don't count because usually air, they are volatilized metal, which only consists of mercury. The others is less likely. Now total metal, they include every single thing. That includes the metal that are soluble, metals that are not soluble and not available to human. So if you want to determine total metal, most likely it will be very high because everything is inside there. Now, by definition, total metal does not means all of these metal they will be absorbed by human. Because why? Some of these metal they're not even soluble. So these are the metals that should not be too harmful to human. Okay. Now, if you look at number four is dissolved metal. Dissolved metal, as the word says itself, these metal that are solubilized in water. In water or maybe in some sort of aqueous phase with a different pH. But either way, aqueous lah kan. Okay. Now, dissolved metal is part of total metal. And usually, for simple estimation of risk factor, usually we just use number four, dissolved metal, to quantify the risk factor. Because once dissolved, once dissolved, this metal will probably absorbed by plants because plants need photosynthesis. So when they are absorbed by plants, then it will be accumulated in plants. Okay, that's number one. Number two, most of the time the exposure to heavy metals are due to consumption of contaminated water, like groundwater, for example. So usually the dissolved metals are the ones that people use to measure the risk factor. Okay? So if you look at here, then the sequence of analyzing is we start with total metal because it doesn't matter uh, what happens. I mean, in terms of variability, because as long as you digest with acid, then you get the whole thing. Dissolved metal, to analyze it, you just extract with water. Yeah, you're going to solubilize those metal, then you analyze it, and that represents dissolved metal. So these are the two things that you need to be mindful. Okay, after you have analyzed the volatilized ones and also the soluble and total metal, then come microbiological samples. Now, these are the ones that is not part of the environmental sampling. Microbiology is not something that I'm going to elaborate further, but it's part of it. Like, for example, if you want to analyze the presence of a certain microbe, like MRSA, for example, in air sampling, possibly COVID virus in water sample nowadays. There's a big issue right now. These are the things that you can put second last, not last, second last, because the last one will be inorganic non-metals. Again, assuming that you don't know what is that. Inorganic means something not carbon, okay, but it's also non-metals. Now, what are those possibly? Okay, coming back to the slides lah. Just now, do you see like all of this? You thought everything is metal, kan? Actually, there's one inorganic non-metal. Do you know which one? There are four metals here. Which one is inorganic non-metal? Anybody? You don't know yet? Okay, so here we have one inorganic non-metal, and is the first one, arsenic. Arsenic is not a metal, for your information. It's a metalloid. So in this case, if you want to analyze this one, then you're going to sample this one last lah. Yeah. So these are the sequence that you need to pay attention lah, and I can tell you lah, you are very good in memorizing, kan? But let's say if I give you the specific name, I'm not sure if you can survive lah. Like these six groups are actually general name, and each group, if you want to go into real life situation, kan, we don't call them VOC, we call them by their chemical names. So I think possibly we're not going to go there at all. We're going to like, I'm going to give you questions with all these things lah, so that you can have an idea. So let me see the next. Okay, by the way, not many description on this slide, but do you know the general idea? Okay, the general principle, why they have such a sequence? Anybody can answer why we want to sample VOC and SVOC first and not the others? Why? Do you, anybody want to answer, or you want to listen to the answer straight away?
Is it because they are volatile, so it is easier for them to disappear?
Yeah, and I think yeah, the answer is correct, but I have a better word for that one. Because they are very mobile. They are very mobile. Yeah. Anything that is very mobile have a tendency to change very quickly, and because of that, they might going to be like having higher exposure, higher risk of getting contaminated. Yeah. So, I mean, the strategy of sampling, the sequence of sampling, we are trying to minimize cross contamination by sampling the most mobile first and then the least mobile. Yeah. So the principle is almost the same as the previous slide. We start with the upstream first, the least contaminated ones maybe, yeah, and then we go to the most contaminated. Because in this case, guys, some of these analyses, they possibly have like lesser conditions to meet. No matter what you do, the result will remain the same. So usually these are the contaminants that are relatively stable. Okay, if you found out lah, the contaminants is relatively stable, less mobile, usually you can sample it last. The one that is very mobile and changes very quickly, and or get contaminated very easily, that you have to see that you have to sample first. Not only sample first, analyze first as well. Yeah. So these are the principles. Strategy is quite straightforward. Yeah. Okay, now done with the sequence. Now, the sampling and equipment device. Now, this one is the technical part. Now, earlier we just finished talking about the management layer, what we call what are the strategies, where do we sample first, which one do we sample first. So that one is done. Now, I'm moving on to the techniques. Yeah. So we're going to see what are the equipments and devices involved. So once again, if we have so much of contaminants, of course lah, many equipments got involved here depending on what you want to analyze. But before that, this is possibly one very crucial thing to remember. I think the sequence here, possibly I should teach you about the sampling technique. I mean, preservation and method is the second part, I would say. But anyway, since we're here, now preservation can be said is compulsory. There's no one sampling, no matter what you say, no matter what you do. Either you sample air, sample soil, or you sample water. Preservation is something that you need to think of. But in water sampling, you can say is compulsory. Because very simple. In water, there are so much of microbial activity that if you do not preserve it, the microbes will still keep on working, and then they change the nature of your water sample. So you have to stop them. Okay, because why? The microbe, when you sample those water, they don't know they're getting sampled. They're still like doing their business as usual. If they are like in the water, they were going to like do all those eating, and then do all the respiration accordingly. So when respiration is ongoing while you collected the water sample, you close it for sure again. So once you close the opening, you restrict the oxygen. And guess what? Without oxygen, the bacteria is still living under anaerobic condition. So what happened to your water? Definitely changed compared to the time when you sample. So these are the things that you need to be mindful, yeah? And to be very simple, I mean, the simplest way to do preservation is just throw everything in the plastic and then put it at between 2 and 6 degrees Celsius at dark condition. There are two reasons. Number one, at this temperature, to be exact lah, less than 4 degrees Celsius, but not less than 2. Do you know why? Do you know why not less than 2? Anybody can answer? Why preservation is never less than 2 degrees Celsius? Why?
Nanti beku.
Not only beku, because when you beku, you're also going to break the container. So depend lah what container that you use. You use glass ke, you use plastic ke. If they frozen, if they turn into ice, then you have to clean up the mess lah. You don't believe me, kan? You can take one plastic container, you put it in a freezer. Tomorrow morning you see what happened to the container. I guarantee you're going to pecah. Yeah. So we don't. We just want them to be at low temperature, but not until frozen. So the best temperature lah, between 2 to 4 degree. Even 6 degree also is not so good. 4. We're aiming 4 degrees. 4 degrees, 2 to 4 degrees. Because at that temperature, the microbial activity will be very, very minimal. So at this temperature, if you can keep it, you can virtually keep it for quite a long time in terms of the stability of the water sample. Okay. Now, what about dark? Why do you even need to put it in a dark place? I think I already told you the answer earlier about the variation. Remember sunlight? Yeah, no, I mean, this time is not about temperature. It's not about temperature. It's about the light. Because some of the reaction depends on activation, either from temperature as a source of energy to activate, and there are some specific bacteria, they also can kickstart a biological reaction by sunlight. There are such bacteria. Not to mention also the cyanobacteria that have chlorophyll. So if you let them have sunlight, then they'll do a lot of things and change in the nature. So having dark bottle or maybe some wrapping, you have to wrap the bottle. If it's transparent, then you have to wrap the bottle. Restrict the light as much as possible, because through that is also one way for you to stop the reaction from happen. So yeah, if you forgot to wrap the plastic, even though you put it at 2 degrees Celsius, something might happen. Yeah. Now, all of which, why do we want to do these two things is to restrict. No, we cannot stop, we cannot stop microbial degradation and everything that is listed right here, but at least we can slow it down. So the idea of preservation is slow down the changes so that you have enough time to analyze them. Because why? We want to analyze the water sample and we want them to be representing the actual condition. So if you do not do the preservation, then by the time you sample, you bring it back, it's already different. So what's the point, kan? Might as well you do on-site measurement. Okay, now that is just one way. The most straightforward and simplest way to do it lah. But there's another way. If you know that a certain method allows you to use chemicals, what we call preservatives lah, you can also use it. Now this preservative can be so many things. They could be acid, could be base, could be biocide. Now acid, for your information, is mostly used as the preservative for heavy metals. So if your analysis is involving analyzing heavy metals, the preservative will be acid. To be exact lah, nitric acid. It's always nitric acid. But sometimes they might use other form of acid like sulfuric acid, depends lah, because when it comes to ammonia, or you want to analyze ammonia in water sample, they might switch to sulfuric acid. Yeah, it depends lah, yeah. Sometimes people also use base, but base from my experience is very rare, but biocide is. Biocide, the name is very specific lah. Most of the time they add biocide to kill germs, to stop the activity altogether. Yeah? So this is how we stop the changes from all this reaction. But also there's one more thing that you need to consider also, proper container. because nowadays there are so many materials people use to make container, either by using glass or plastic. Now, I think you possibly have heard lah, in order, I mean, the best option to store drinking water. Okay, let me ask you, to store drinking water, what would you prefer for health reasons lah? Yeah, is it glass, plastic, or metal? Which one do you prefer? I think this is out of the sampling. I just want to ask you general knowledge. If you want to drink water and you want to store water, do you store in glass bottle or plastic bottle or metal bottle? Anybody wants to answer?
Plastic.
Glass, yeah.
Yes, any material that's not plastic.
I think yeah, but you still haven't answered the question, isn't it? Any materials that is not caustic. Not what is it? Okay. Can I say that you want to choose a material that is the most stable and doesn't change too much and then leach the contaminants to your water? Can I say that? Yes, can.
Yes, yes.
Yes.
Okay, now for those who answer glass bottle, you're absolutely correct. Because why? Most of the glass that I know lah is quite stable against heat. And the process of manufacturing glass, once you have the glass, they are chemically stable, except alkaline, very, very alkaline condition. But I'm sure you're not going to drink sodium hydroxide, guys. So that's out of the story lah. So yeah, if you want to have a very healthy lifestyle, you should actually use glass bottle to store your water. Okay, not metal, not plastic. Metal, I think we all know lah, it corrodes. Dia keluarkan karat. And also sometimes if metal starts to react with oxygen, they might leach. So sometimes when you drink from metal container, you might discover that the taste is a bit sour. Kan? And then you know what's worse. The sour taste is probably not due to the hydronium, the acid. It's probably due to the metals that dissolve. So that's why when you drink from a metal, an iron cup, you're going to taste soury taste. So that is the metal taste lah. Now what about plastic? Plastic, for your information, is very broad. Don't think that the plastic that you are using is like the drinking water bottle. So yeah, you're right. If you're talking about drinking water bottle, their plastic is not the most durable. Unfortunately, you have to know this lah. And the process of manufacturing plastic, they put heavy metal as stabilizer. Sometimes as catalyst, sometimes as stabilizer. So that's why like, if you have a choice lah, don't drink water, I mean bottled water lah. If you can, you drink from boiled water from the tap also can. Bottled water from time to time okay lah, but not too frequent because the quality is not there. They might leach out heavy metals. They might also leach microplastic and also some organic pollutants because after all plastic is made from monomer. Monomer, I can tell you lah, it's if the monomer exists, it's VOC or SVOC. So also contaminants to you. So drinking water, bottled water is not really a good idea lah for information. Now, what does that have to do with sampling? You might ask, kan? Now, I want to ask you, from your experience until now, have you ever seen any metal being used, any metal bottles being used in environmental sampling?
No.
Okay.
Oh.
I think for the reasons that we already discussed just now, because metal corrodes very fast. And then when you have water inside, water actually serves as an electrolyte. And you have bacteria. Bacteria also releases acid. That actually helps the corrosion. So metal is a big no-no, I would say. But for some reason, I don't know, maybe there's a like metal container, but most of the time they don't. Now, so that comes to two materials, glass or plastic. Kan? Which one do you think is the most preferred materials in environmental sampling?
Glass.
Glass.
You prefer glass, yeah?
Glass.
Okay,
Glass.
think of this lah. You need to sample maybe 200 samples. So you need to prepare 200 glass bottle then. 200 glass bottle is a lot, you know. How sure are you going to come back with 200 glass bottle, not pecah, not everything? Do you see the idea? I know. You want to say glass is best, and I also agree. Glass also is best. But in today's world of environmental sampling, you possibly need to climb mountains. And you cannot bring 200 glass bottle just like that, kan? And then at some point you might slip and fall down. So glass, even though it is stable, but it's not the preferred choice. So that comes to plastic. But like I said, plastic also have many types. And for your information, there are some plastic that are very durable. They might last for the duration of your sampling, but possibly not lasting forever. So for the purpose of water sampling, I can say lah, plastic is most preferred than glass, although glass also might comes in, depending on condition. So we can put it this way lah, proper container depends on what contaminants that you are dealing, and also where is your sampling site. If your sampling site is very rugged, you need to climb, and you can possibly fall down and have a risk of breaking glasses, then plastic is preferred. So don't restrict yourself to glass, because frankly speaking lah, practically plastic is the most preferred. Okay, now there are things that you need to manage. If you prefer glass, you have to manage things accordingly. If it is plastic, then yeah, you have to manage it accordingly. Now moving on to the next part, the equipments. I don't know what to say lah, because why? Uh, does everyone actually enroll water resource technology? Does everyone here enroll water resource technology? Have you learned? Are you all enrolling water resource technology? This subject. Are you all learning this subject?
Yes.
Yes.
All of you. If not all, almost all, I assume that almost all of you learned that. I just have one question now. Which one have you seen in the lab? Which one of
We
these
study this sem, sir.
you studied?
This sem.
Which one? Or is it not here?
No, we've
Never
never
see.
Okay, now I'm not sure what you have learned in water resource technology, but I've taught water resource technology myself before. And actually, we have one. Out of these three, we have one. I'm just not sure whether you've seen it or not. You haven't lah.
No.
Okay.
No, doctor.
Okay. By the way, next time lah, next time when you're into water, into the business of collecting environmental water, you were going to use C. C is what you're going to use. The one that our faculty have, our department have, is B. We have, okay, and then A is possibly the least used lah, pond or grab sampler. No, I mean the main reason is not too practical. If you're going to sample stream water, if it's shallow, you just jump into the river. Pond sampler is like not too practical, so that's why not really something that we need. Now we do have B, okay, and in fact B in FSG, this whole thing is intact and it is attached to a long pole. So what does people do is that at the bottom of this weighted bottle sampler, there will be one reagent bottle attached to it. So you screw tight, and then there's a pole you attach to it. So you throw the entire bottle. So you take the pole attached to this weighted bottle sampler, and then you dip it into the river. Once it is immersed in the river water, you just pull a trigger, and then this one will going to be released. This cork will open, and then all the water will flow in. Once it has finished flowing in, then you just take out the entire thing. There you go. You have one reagent bottle full of river water. But then again, it is still also not practical. Do you know why? The pole, the longest that I have seen is possibly 1 meter plus. Longest possibly 2 meter. Because if the pole is too long, it will going to snap into two. So B also is not too practical. Now C is possibly what you're going to see more often in the industry, especially in the enforcement agency like Jabatan Alam Sekitar. They all uses this one. If not this one, is the other type which is like used perpendicularly. Because why? This whole thing is more or less the same. They have one trigger where they can pull and release water inside, then you pull up. Now why this is so practical is that there is a string, there's a rope tied into one part of this camera bottle, and then once they have lowered down into the river, they can lower down into according to the depth that they want. And then once they reach that depth, then they pull the trigger and then collect water sample from there. So camera bottle is the one that people use outside, but unfortunately our faculty did not have not purchased this one, so you don't have an idea how this was done. Yeah. By the way, now if you want to collect very shallow water, you don't even need to use all three of this. Just what? Jump into the river, use your hand, use your bottle, open the bottle and collect just like that. Yeah, if you don't need to use this equipment, it's not compulsory. If you can use your hands and you collect, you just jump into the river. Simple as that. But of course, not all rivers are too shallow, isn't it? So that's why C is the one. And sometimes, do you know where people use C? Sometimes they use C on a boat, so you can see how deep it is the river sometimes, or maybe a lake. Oh, by the way, the C also may be used in marine water sampling as well, yeah, for information. So once you have collected all those water, then what you do? You put it inside a bottle lah. So we don't use the resealable bag, So usually the containers that people use to store water sample, they are a bit rigid, uh, quite durable against knocks or minor knocks and falls, so that they don't break apart. So we don't use soft plastic, we use hard plastic bottle. So once we have filled it, then close it according to the requirements of the contaminants. And then what? Put another plastic bag, seal it again, and then put it in ice water. So this so-called ice box, inside here they have a lot of ice. And once they fill it with ice, they also pour water. They possibly won't going to pour very full, but until every single bottle is completely immersed, they have to rendam betul-betul lah all the bottles. And I think with this setup, the condition is nearing single digit degrees Celsius, if not 5, maybe around 7 and 8. I mean that is good enough already, yeah, as long as they are not warm. So that's it. This is how you do your sampling, which is why, in reality, if you want to do water sampling, one ice box is not enough. Initially, okay, sad story lah. Initially, our department have three. Our department have three such ice box, but due to theft lah, I think there's only one left, and that one, I don't think you can even collect more than 50 samples. I think the maximum is 20, 30 only. So yeah, if you want to collect 200 samples, then you have to bring more ice box lah. Yeah? Oh, by the way, do you know why we use only the good quality ice box? Do you know why? Because if you use polystyrene, I know there are like cheaper ice box, the white color polystyrene, 10 ringgit per one. You can use that. But imagine you are storing water and they also break very easily. You have a knock, then all the ice water gone, then what? Your sample all gone lah. So that's why we don't use cheap things. We use a durable icebox plastic. We use durable sample bottle, things like this lah, yeah. Okay, now comes the preservation. So just now I told you that there are many things that people use in preserving things. So these are the details lah, yeah. So if you want to memorize, I think it's also good for you to memorize, because after this is what you do. I mean, frankly speaking, you can say lah, most of these preservatives, they are quite standardized. Like from preservation of metals, you use nitric acid. What pH they want to achieve? Less than 2. So most of the time, yeah, when you use this nitric acid, we're going to use the concentrated one. Just 1 or 2 drops is enough, nitric acid. Whereas if you want to analyze this low level, low concentration organic compound, there might be a risk that this organic compound might stick to the wall of plastic bottle. That is always the case. Is if even if you use glass bottle, this organic compound will still stick to the wall. So what do you do? You use a Teflon line, preferably like Teflon vials. There are vials or containers that have Teflon lining inside. Do you know what is Teflon, first of all? Do you know what is that Teflon?
Oh,
Girls, do you know what is Teflon?
No.
Oh.
No.
Okay.
oh,
Oh.
Okay, now I think possibly you know Teflon, but you don't know that it's called Teflon. You know Teflon, but you don't know the name is Teflon. Okay, now I'm sure you have cooked before. The non-stick one, the black colored one, those are Teflon. Non-stick cookware, if you can feel some slippery, those are Teflon. But those are only on cookware lah. Because if you have seen a real Teflon vial or Teflon bottle, it's actually white in color. Teflon is just like any other plastic. It's transparent, possibly a little bit whitish, but the reason why Teflon is used here is that nothing can stick. So it minimizes the error of like contaminants stick to the wall. Everything is coming out in the liquid phase or whatever. Yeah. Now that goes to the oil sample as well. So absorption to plastic is a risk. So possibly you can use glass bottle. But once again, if you can choose Teflon, use Teflon. Yeah, those are the things that we try to use to avoid contamination or some loss due to absorption. VOC and everything. Now, for all those things that can volatilize, you can see that there are two strategies. Number one, you avoid headspace. Do you know what is this? Avoid headspace. Do you know what is headspace, first of all? Headspace.
No.
Okay, now, well, first time that I learned headspace is during analytical chemistry. Okay, now for your information, headspace is the air, the air between the surface of your liquid sample and also the top of your cap. So once you have collected water samples, kan, there are like some parts where it is not filled with water, kan, that air, that space is called headspace. Okay, now why do we want to avoid this headspace? Because that space is the only region that the VOC can go to. Because VOC can volatilize, kan? So if they volatilize from liquid, they will become gas. So they will go to end up in headspace. So in order to avoid those things happening, usually for any liquid samples that you want to analyze VOC, we will fill until the top. We will fill until the top and no air at all inside the bottle. So you remove all the air and fill it fully with liquid, with water sample. I think the same also goes to any water samples that you want to analyze ammonia. But ammonia, apart from having avoiding headspace, ammonia have another option, preservation. Ammonia can be preserved by sulfuric acid. Just now what I said, ammonia can be preserved with sulfuric acid is the same, less than 2 pH. Because why? If you have sulfuric acid, this sulfate can attach to the ammonia. So if they're attached, then they no longer volatilize lah. So that's why sulfuric acid is preferred, not nitric acid. And so on and so forth. So I think what I'm going to say right now is that the preservation, the options, and also the chemicals, they are so many. Can you remember all of it? The answer is you can if you are a chemist like me. I know everything about this one because I learned this from day one when I learned analytical chemistry. So that's why I'm a bit surprised lah, that when you learn analytical chemistry, you don't learn everything. But it's okay. It's okay. It's not too late because you're learning in environmental sampling. So don't tell me you don't want to learn this lah. You must, because you yourself, you want to call yourself environmental technician kan, you're going to go out and collect sample, water sample. These are the things that you wajib, you have to know. What are the preservatives that you should use? So if I say you have to know, that means it's coming lah in your test and exam. I know some of you might take it like might feel like it's hard because it's chemistry, but I mean what's not chemistry, kan? So take your time lah. I mean if you want to start, yeah, maybe you can prioritize this table and then you can study later how you strategize your studying. But these are the things that you need to know lah in terms of preservation. And then furthermore, water sampling container and methods. So like I told you just now, apart from Teflon to handle all those organic contaminants, most likely we're going to use plastic container and not glass. So you can see here, HDPE, polyethylene, high density polyethylene is a material that we should go to. And mind you, for example, for your information, uh, these kind of bottle, they are quite durable. It's not like it will going to leach out everything in at high temperature. Sometimes these things can last with high temperature as well, because they're specially made. So no worries lah. Just don't use your mineral water bottle lah to collect water sample. That's all. Because it's HDPE, they are very dense, they are very durable, and they can last with high temperature. And one more thing, they can be reused. You can bring it back, wash, and they can reuse it. But once again lah, what do you want to use as usual lah? If you want to analyze metal as usual, the nitric acid has to be here. But there are like certain things that you need to follow also, like the filtration. Now, some of the analysis, in order to be accurate, they might require filtration. Like for this one, it requires filtration with 0.45 micron filter. And the reason is that in order to measure dissolved metal, you have to filter first. Because after filtration, it is said that the metals that are complex will be removed away from the water sample. Okay, these are just extra information for you lah. If you want to know further, these are the things, yeah. And so yeah, I think I have nothing more to explain to you, because I think you can read for yourself, and I think you might want to have like a break of some sort. I don't want to explain these things lah, because I have already explained the general part is just the chemical name and also the specific name of the material of containers that you might going to use with the contaminants of interest, the analytes that you want to determine. Okay, use your own time. These are examples. I know you can read. I don't need to read it for you. So I think I will come to this maximum holding time before I can let you have the 5-minute break. Okay, so let's finish this one now. What is mean by maximum holding time is that how much time that you have after sampling before the water samples goes back. So you can say that after you collect the samples with the proper preservation and also the containers that you have, some of these water samples might not last the same time as the others, simply because the contaminants, they are different. Like I told you earlier, some contaminants like VOC, they volatilize very quick, or if they don't volatilize, they might be consumed by bacteria, microbes. Microbes actually can consume VOC as their source of energy. And with that, if the contaminants can change very rapidly, usually they're going to have a very low maximum holding times. And what does that mean? That means you have to pandai-pandai lah. Once you collected a sample, you know that they have a very short maximum holding time. You should prioritize the analysis of the sample. Yeah, so these are part of the planning, right? So you can see lah, of all those contaminants that you want to analyze, and with all the proper preservation and sampling techniques, some parameters you cannot wait. You have to analyze straight away because they change so fast. It is your best interest that you measure straight away. So let's see at the left hand side lah. ASAP, as soon as possible. That means you have to measure, you have to analyze it as soon as possible. Things like pH, I know you can change it in a split second. So that is why in water resource technology, you have one equipment to bring with you wherever you want to go, and that is YSI kan. You remember YSI? Have you seen one before? Have you seen YSI in FSG?
No,
No.
sir.
Okay, maybe you can ask.
No.
Who is teaching water resource technology? Dr. Nick, is it? Is
Yes.
it
Yes.
Dr. Okay, apart from Dr. Nick, I think Dr. Nadia also is teaching wastewater. If you happen to go to wastewater lah, you can ask either one of them to show you the picture or the video of YSI. YSI probe is a device in a briefcase. It's like a detector, like a pH meter, portable pH meter. It's a portable meter, not pH only. It's a portable meter where you can measure pH, dissolved oxygen, salinity, electrical conductivity, total dissolved solid, temperature, 6. Taken these are the 6 lah, but I was told that some of the advanced YSI can measure even more than that. So that depends on what electrode that you're having. And guess what? Again, we used to have two. We have to have two YSI. One breaks down because student use it the wrong way. And then that left us with one, the only one left, and that costs us, if not mistaken, 30,000. 30. Wait, is it 30,000? Is it the cost of one motor or one car? But it's almost the same lah. One car is the cost of YSI. It is that expensive. And yeah, usually in environmental sampling, that is a must lah, because you measure it straight away. Okay, and then what are the other things that you can wait and you can bring back to the lab? So these are the things lah. You want to do BOD, of course, you cannot measure straight away, kan? So you have to bring back, wait for 6 days. BOD, you're doing. I mean, what is the duration of doing BOD? 6 days or 4 days? I forgot. BOD, how many days? You want to do it? Hey, how come you cannot answer? Because you told me you're enrolling water resource technology. You should have known what. How many days? Hey, voice nyao je. Don't know.
We haven't learned about it yet.
Okay, you just wait. Okay, you will learn about this one. It is called biochemical oxygen demand, and if not mistaken, at least 4 days lah. 4 days is not the standard method. I think you probably need more days than that. Yeah. And then there are other things that you can do like turbidity. Turbidity sometimes you can measure straight away with YSI. So these are the time that you can wait lah. And more so, if you want to analyze heavy metal, total metal, for example, the entire metal, no filtration, it can last for 6 months if you want to wait that long lah. But usually we don't need to wait that long. After you bring back your sample, it is said lah, it's your best interest to measure, to analyze all those samples within the first 7 days. From my experience lah, I did sampling before. The best is you analyze immediately, straight away, clean data, very predictable as expected. But after you wait for 7 days, the pH will first go different, very different, and usually it will go down, very acidic. If it goes very acidic, that means bacteria is there lah. Okay? But these are the things that you need to consider lah. Yeah. Now there's so many contaminants right here that you need to consider. When once again lah, do you need to memorize? Use your common sense lah. It's just like, I mean, environment sampling as well. The trick is that if the contaminants is very mobile and changes very quickly, then most of the time the maximum holding time will be very short lah. Yeah. But if you can remember like all these maximum holding times, you can remember that one. But one thing that I need to highlight here is that this maximum holding time is described and issued by APHA. Okay, APHA is not the same with Jabatan Alam Sekitar Malaysia though. So sometimes lah, yeah, sometimes these maximum holding times may be different according to different bodies. Yeah. So apart from APHA, there might be DOE that might have their own maximum holding time. But I was told that APHA is the strictest lah. So that's why I put APHA right here. Okay. So with that, these are the examples of bottles where you can see for yourself. So I'm going to continue with the quality control and also quality assurance for field sampling. As far as water quality concerned, there are a few samples that you need to consider and you need to plan out before you embark on your sampling journey. Okay, now first question is, what is quality control? I think this is not the first time you heard. At least in the first lecture I already told you what is that, so I'm going to go through this really quickly. You can say that these are the technical or the actual procedures in order to maintain the accuracy of a result, to maintain the quality of your result. So these are like the technical sides. Usually is the standard operating procedure we're talking about. But in this so-called operating procedure, there are specific things that we're going to go through after this, in which I'm going to like elaborate a few examples of samples that you need to take, apart from the actual samples. Yeah. So why do we need to control the quality? Now that is because, as we learned just now, variables. There are so many variables that can change the quality of your water sample. So in order to prevent that from interrupting your actual intention, you will try to minimize those variables, or at least try to minimize the error coming from these variables at least. Okay, so it is very important for you to identify these variables and how does they affect the data quality. Okay, because once you know where are the source of this error, then you can quantify them. And even though your data is like subjected to all these variables, if you do understand, you can make corrections and your data will still be applicable, acceptable, admissible, they call it. Yeah. So as I said to you earlier, it's the error that coming from all these environmental variables, like it from temperature or whatnot, but most likely is due to the nature of the contaminants as also the matrices. So the objective of this quality control is to maintain the accuracy. Okay? Make sure that we can have like as accurate as possible the representation of your sample water, and then so that when you measure it, you have confidence that your data does represent the environment, the water that you intend to sample, and the data that you have measured is accurate. So it's paramount that you know the actual result and having the confidence to believe so. Yeah. And in terms of the quality control, they are evaluated in the so-called PARC parameters, PARCC parameters. And I think these PARC parameters I've also elaborated in our first lecture. Possibly you don't remember, but I'm going to take you through lah. So what is PARC? Precision, accuracy, representativeness, completeness, and comparability. All of which they are the essence or the key parameters in order to define the error and also variability of your measurement. So if you do have all these parameters, then there should be no problem for you to understand why your data is such and such. And then from that understanding, then you have confidence to believe that your data is indeed accurate. Okay. So you can see it's a level of confidence in your data. If you know how the error plays about, then you can safely say that, okay, my data is confident. And in fact, there are like certain confidence level as well, if you want to know. Some people have a confidence level of up to 99%. That is possibly the highest, but the acceptable one is 95% confidence level. Anything less than that is not admissible, at least for law enforcement. Yeah, 95% is what we can accept, yeah? or higher confidence level. So the QC system are used to provide constant checks on sensitivity and accuracy of instrument, maintain instrument calibration and accurate response, provide real-time monitoring of the instrument performance, and monitor long-term performance. So all of which, most of the QC involves the use of instrument. Okay, now, although in this slide they say that instrument is what they look at, because why? Instrument is used to measure. Now, in order to have a confidence in those measurements, you have to know exactly that, okay, if they measure A, you are expecting to get A result. Same, that is what you get from what we do on calibration. If you calibrate a certain things, and these things, like for example, you're calibrating a balance and you're putting 1 kilogram on the balance, what you should see on the display panel, exactly 1 kilo, something like that lah, the calibration. So these are the things that we always do, no matter what instrument that you use, whether it's for measurement or for preparation. Sometimes equipments that we use for preparation are also subjected to calibration as well. But most likely it's subjected to the instrument that you use for measuring parameters. pH meter, the balance, these are the one. Now, so QC also is part of it. How do you measure? How do you calibrate? Is also one thing, because there's no one way to calibrate one instrument. There's so many things, but one thing for sure, if you want to calibrate one instrument, you always use standard. I think possibly we're going to have a few examples that we can go through. Yeah. So calibration always involve the use of standard. Yeah. Okay, now what about sensitivity, the ability to discriminate between measurement response. Now, sensitivity is another criteria. To measure how good is your instrument. Uh, Now, I would define the sensitivity is how small is the response, how small um, that a instrument can measure, can detect. Because some instruments, they are not that sensitive, and if you have a very small, very low level of contamination, if you use that instrument, they possibly won't pick up anything. They're just like reporting not detected, not detected level. It's not zero, but not detected, meaning that the contaminants is there, but the instrument have no ability to detect that small amount. So the term is very important. It's not zero, it's non-detected. Yeah. And similar words that people use here is like possibly detection limit. So some instrument also, they might have a limit in detecting small, very low level of contamination. I take example. In terms of measuring heavy metals, there are two. You have ICP-OES and ICP-MS. The detection limit for ICP-MS is parts per billion, or microgram per liter. Whereas ICP-OES sounded similar, but the detection limit is much more higher, much more lower, I would say. Lower, yeah. Because for ICP-OES, the detection limit is parts per million, ppm, or milligram per liter. Okay, so these are the examples lah to define what are detection limit of the measuring equipment. So yeah. And also, yeah, about the detection limit, also that also depends on the instrument. Not only the instrument, but also the methods, because some methods they also have limitation, very similar to the instrument, and also the measurement range, extent of reliability of the instrument readings provided by the. Now this possibly is not too applicable because usually the reliability of the instrument readings is depending on the instrument itself. But in order to overcome this problem, we also have like QC procedure in place just to see how consistent. You see, instrument when they keep measuring for such a long time, they may change or they may like change in terms of the measurement. They are no longer accurate because everything changed. But in order to measure this change, QC procedure can be implemented to measure these changes and then also to correct it. Yeah. Also, now, I'm going to go through this quickly, lah. Quality control. Now, in terms of field quality control, these are the things that you can do in order to measure change and to minimize the error. Now, I want to introduce you, if you haven't heard about these so-called samples, the type of QC samples is what you need to pay attention lah. And more so, if you want to plan out your environmental sampling plan, these are the things that's compulsory, wajib. All these QC sample. It could be field duplicates, split samples, performance evaluation samples, and tricks, and also equipment and cooler temperature blanks. So you can say lah, in general, there are duplicates, there are standards, there are blanks. Blanks is usually having a lot on, yeah, when you want to go for quality control. Now, each of these QC samples serve different purposes, in which after this we have different slides for you to elaborate. Yeah. So apart from these QC samples, you also have frequencies. I would say maybe replicates is what they meant here, not frequency. The frequency of you of having repeating the sampling. So I would say replicate probably is what they meant. Acceptance criteria, the control limits. So these are the things that are related to the limits of your objective. Let's say if your objective is trying to detect a very low level contamination, then you have to use the proper procedure lah kan. You cannot use a very crude procedure to analyze a very fine and to detect very minute, very concentration. So depends, yeah. Corrective actions that will be done when acceptance criteria are exceeded. So things might happen that when you go and sample, it did not turn out as you expected, and maybe that the concentration is lower than expected, for example. Then what do? What are the countermeasures that you need to do? Do you dilute or do you change the QC? And from the QC, can you actually measure the so-called sensitivity? That these are the things that maybe QC samples can help you in measuring the variation and also the detection limit of one methods. Yeah. So similarly lah, field measurement or also laboratory. Now this one is more into the analysis part. Now you can see some similarity, although not exactly the same, the type of QC samples. You also have duplicates, but this time is lab duplicates, matrix spikes, performance evaluation sample, method blanks, and surrogate. So these are the things that mimic the QC samples for field sampling, but I included here simply because after you sample, then what do? You always go and analyze them. So I mean, these are the things that's applicable. But what is interesting is that they look similar. You will have blanks, you will have duplicates, and you will have standards where you measure. Yeah. So these are the similarities that you have to, yeah, that you notice lah. Yeah. Okay. Now everything looks similar, so I think I'll jump straight to the examples of QC samples that you might want to remember first before you implement in your sampling plan. Okay, number one, field blanks. Then the other one is rinse blanks. Uh, sounded very similar, but they are different. I think after this, there are slides where we can explain that. Now, apart from blanks, we have spike sample. So what is spike inside here? You might ask. The standard. We spike standard here. A known concentration of something. You spike it inside a sample and you bring it to the site just to see how they respond, how the material in your container responds, and then you measure just to see if there's any possible cross contamination or any variation due to the materials in your container. Yeah, this might happen as well, but if you have spike samples, then you know whether that is affected. Yeah. Split samples is where you collect one sample and you split into two, and then you measure differently, or maybe using different operators or maybe different instrument. So this is split. Blind samples, not really sure, but hopefully after this there are like slides that we can explain. So these are the examples that you should have before you even go for your sampling plan. In your sampling plan, you must describe how you do it. Okay, let's start with blanks. Now, blanks is compulsory. No matter what you do, blanks is a must. No matter if you go and collect field sample, even during your analysis using any equipment, blanks is a must. Yeah. Now, in the field, for example, you're going to use a container supplied by the analytical laboratory, collect a sample, analyte free water, distilled water. Usually, we just put distilled water in that container and then bring it back. So in the field, this is like, why do you want to do it? Because in the field, when you put in distilled water, by the time you carry back into the lab, what do you expect? You expect distilled water inside there with no increase of contamination. Kan? So what is the purpose of we doing this? Now this is to mimic, okay, to mimic whatever that you do in the field, but only using distilled water, something that you should not detect anything. Okay. Now, if you do that, you possibly can pick up any like factors that might going to introduce contaminants into your sample water. Now, you don't know what is the concentration in your sample water, isn't it? Because it is unknown. But in distilled water, quite safe to say lah, nothing should be inside there. So when you put in distilled water in the site, close it back, and you bring it back, in the lab you should detect zero, nothing at all. But if you do detect something inside there, most likely is due to field contamination. Either when you're trying to collect the samples, and then somewhere in the field there might be a source of contamination, and that's why it will be picked up in your field blanks. Yeah. So the purpose is very important, and it's usually part of it. Yeah. Uh, Now, if the preservative is applicable to the analyte, so in this case, you also need to follow accordingly. You just fill in distilled water. The rest of it, you just follow exactly the procedure for sampling for the environmental water sample. Exactly the same. So you treat the same as the sample collected during the designated sampling period, and then you submit the blank for analysis for other samples from that field operation. Now, it is said that the purpose of having field blanks is to measure the possible contamination during field trip. However, there are like some other blanks related to field blanks also. They are there to measure, is there any contamination coming from the container itself. So just now I told you HDPE, kan? So HDPE, some of them, they are manufactured by a low graded materials, and they might go to leach heavy metals. That might happen. So field blanks might do the job, but I think that that one is under this one, equipments or rinsate blank collection. So let me elaborate. Yeah. So rinsate. So in order to detect any contamination coming from the glassware, the container, or the equipment, I think this blank serve its purpose lah. So how do we do it? Okay, we rinse the equipment to be used in the sample with distilled water after collecting the sample. So you treat it as the same way, just like the field blanks, but the purpose of this rinsate blank is to detect the contamination from equipment. either from the container or from the measuring instrument that you brought along with you. So don't be surprised, sometimes the source of the contamination is only from the container itself. Yeah, and it does happen. Yeah. So rinse it blank, apart from the field blanks, compulsory lah in your field trip. Yeah, in your sampling plan. Okay, now the next one, duplicate or replicate sample collection. Okay, let's go through first. Okay, two separate samples are collected at the same time location using the same method. So this is where you are said to be at one same location. So once you finish collecting one bottle, you collect the next bottle. Same method, same location, same time. This is what we call replicates. So in terms of statistics lah, I think you've been taught like at least you must have at least two replicate. Well, the answer is the more you have, the better. But depends on how deep is your pocket lah. If you have a lot of money to buy the containers, then okay lah. You can collect up to 5 replicates if you want to, but it depends on your strategy. Like for example, if you have like a very high risk of losing or very high variability in terms of these samples, it is best for you to collect as many as you possibly can lah, the replicates. Yeah. So the same thing lah, yeah. It's just this one is on the sample, environmental water sample. You just collect more than one. How many? There's no limit. As many as you like, depending on your money lah. Yeah. Now the replicates determines representativeness because why? At times, when you you collect the first bottle and you collect the second bottle, logically speaking, when you analyze these two replicates, their readings, their parameter, their data coming from these two replicates should be the same, isn't it? Good. So in this kind of understanding, usually we will analyze this replicate just to see how stable and how similar they are. We're going to see their precision of the data, because if they're coming from the same spot, they should have having the same data. Of course, they might not be exactly the same. There might be some tiny little variables there, but the point is that we want to see how stable is the measurement. Yeah. And of course the representativeness, because why? If let's say out of those two replicates, one is different, or one of them is very, very different, you might ask, are you collecting the same sample? Because why? You're collecting from the same location. How come they can be so different? So these are like a fail safe lah for scientists. They will collect more than one sample just in case one becomes really bad for some reason they don't know. At least they have other replicates to back up. Right? Because if you have 5 replicates, if one goes very, very wrong, have very, very different data, you still have 4 more replicates to back you up. And if those 4 replicates, they are very similar, then you can exclude, you can reject the one that is like very, very different and keep on with. So that's why replicates is your best interest, that you can collect more, you collect more lah, yeah. Okay, so that is the same point that we have explained just now, the representativeness. So I'm going to skip and go to split and blind sample. So what is split sample? A sample is collected and mixed thoroughly. The sample is divided equally into 2 or more subsamples and submitted as a different analyst to different analysts and laboratories. So why we want to do this? Now, although here you say they want to determine precision, but here the split samples, they serve many, many functions. Either you do it as field split or lab splits. Now that is because if you do and split the same sample, which technically supposed to have the same characteristic and therefore same data, you'll be surprised that when it is analyzed by 2 different individuals, the data might turn out quite differently. Do you know why? Maybe the first operator is very skilled, like a analytical chemist lah. So the result comes out A. Okay. and then the other the other operator possibly is not very skilled, and then they have a different data. Now, who do you want to believe, kan? Because why we want to do this is to prevent bias, because some operators, they might have prior knowledge, or maybe they have some skills that they have, and they can conduct the experiment, the analysis very effectively, and therefore give you the accurate result. However, there are many factors that might place in here, and they give you different result. Skill set is one, the other one is biasness. So in order to prevent that from happening, it is also a good practice lah that once a sample is collected, we will split it and put it as blind sample and send it to different operators or different laboratories so that they can analyze it independently. And when you get back the two samples, you have the confidence to know that they must be the same data. If they come back the same data, then okay lah, we rest the case. If they're different, then probably further investigation can be conducted lah. So the main purpose here is to analyze and to determine precision. Yeah. And then what is spike sample? Now spike sample here is to put a known concentration of analyte into a sample, either during field sampling or during lab preparation. So even before you go to the field, you already put the spike sample in a container. And then during field trip also you put it in. And sometimes during analysis also you use spike sample just to see how the standard holds on in the water sample. Now once you put the known concentration, and when you analyze it, you should get back the same concentration as you spike. Like let's say for example, you are spiking 10 ppm, 10 ppm of lead solution, for example. During analysis, you can expect lah to get back 10 ppm, 10 ppm from the spike sample. So what is the use of spike sample is we are determining, we can actually calculate the accuracy. We can determine the accuracy of this method, of this QC method, by determining the percent recovery. Now I have a question for you, for all of you. Have you learned how to calculate percent recovery? Yes or no? Have you learned?
Mm, no, because this is my first time hearing about percent recovery.
Oh my God. You know
But
what?
doctor, I don't know about other people.
Okay. Okay, now let me ask you, have you taken analytical chemistry? Have you taken analytical chemistry before?
Yes.
Okay, so so I think that justify when I say oh my God lah. You know why? You know, I was also an undergraduate student before, and I've learned this in analytical chemistry. So if you say you haven't learned percent recovery, then that means you haven't learned analytical chemistry, for your information. Okay. But don't worry, don't worry, because if you haven't learned, then you should now. Okay. Because in order to determine accuracy, it's compulsory for you to determine percent recovery, and usually lah, percent recovery that we prefer is 99%, because 99% means if you put 100 ppm, you get 99 ppm, for example lah kan. Okay, so that equates to 99% percent recovery. So these are the things that we actually analytical chemists determine, yeah, to determine accuracy. So if you don't know how to determine percent accuracy, then it's good lah. You can look at the textbook. I'm sure the textbook have a lot of questions and how to calculate percent recovery. So you go ahead and refer to your textbook. I don't think time permits us to talk too much because I think we have 5 minutes. So let me see. 40. Yeah, I think 6 to 7 slides to finish. So let me finish it, yeah. Okay. So basically, I think those are the things that I need you to know. the QC samples. Make sure you know what are they, why are they for, and how to determine them. Yeah. So you can expect lah in exam, you can wait for that question. Okay, comparability. Now, why do we need to know that? That is because when you have an equipment to measure things, there might be one or more equipments that you can use. So like for example here, you have UVVs, you can also have portable spectrophotometer. Now the question is, which one is better? Now I cannot say, because why? I personally would going to prefer UVVs because they are very stable, very high detection limit. So I mean, it's up to you. If if the experiment requires you to have this portable spectrophotometer, yeah, you can also use it. If the analyte changes very rapidly, so it all depends on the requirement. Yeah, but if you can, I would suggest we run. I mean, you analyze just like the split sample earlier. Once you split it, you can analyze it using different equipments. Like for example, this one, spectrophotometer or UVV spectrophotometer. They are essentially the same, only one portable and one desktop. But of course, lah, UVV spectrophotometer is said to be the more accurate ones. Yeah. And then what is completeness? Completeness is the percent comparison between the amount of data intended to be collected versus actual amount of valid usable data collected. Now this one is usually in the QA the QA procedure yeah. Well, I think this one I won't going to elaborate too much. Possibly you can read further due to time constraint. So basically, what is the key concept of QA and QC? It's a sample design and the validity of data. So when you design this sampling plan and also have most of the time together with analysis plan, you have to think of how big is the sample size, number one. And once you have determined the sample size, you also have to determine um, the requirement of QC samples like blanks, replicates. So these are the things you have to take into account, because although you want to have as many as possible, the replicates, sometimes the budget does not allow you to do it. So you have to think, okay, what are the minimum requirement of your objective versus the design that you are allowed to do it. Okay, so sampling design also you need to address how sensitive is your data. Are you going to report your data in ppm or ppb? Just now that I told you, if you want to determine your answer in ppm, then probably you can just use ICP-OES. Yeah? If it's ppb, then ICP-MS. Okay? So validity of data. So during validity of data, you're going to discuss first of all, you're going to determine all those percent recovery to measure the precision and also the accuracy of your data. So most of the discussion regarding validity of data revolving a lot on the interpretation of all your QC samples earlier. But of course, I think you should know because why? Usually the discussion about validity of data is exactly the error analysis. If you still remember, I give you a talk on how to write a proper lab report for soil science and analysis. The part where it is involving uh, data analysis, where you discuss accuracy and precision, this one lah. So you can imagine that is that one lah. Yeah. Okay, so I think this one I have already mentioned most of them, so I don't think I want to repeat. Elements of QAPP. This is mostly on the quality assurance layer, and I think this one you can read it yourself. And so these are the tips yeah. Final two slides. These are the tips. What are the things that you need to consider when you are reviewing QC sample results? So these are the things. So most of them we have already discussed earlier. Okay. How many duplicates do you want? What are the purpose of having blanks? How much blank? How many replicates? These are the questions that you need to ask yourself first when you do your environmental sampling plan, because there's no definite right or wrong answer. So that's why I know you may have a template that is given to you earlier, but you do not need to copy exactly, because after all, it comes back to your objective. Okay, so it's up to you. Yeah, how big is your replicate? How big is your duplicate? If you want to check your answer, how do you want to check? You check using different labs, or you want to check using different instrument. Both also can be done, but you have to describe clearly in your environmental sampling plan. Okay, but most importantly, why do you want to do it? You see, it's not like for fun. We do field blanks or lab blanks because we want to detect is there any cross contamination. Yeah, and if you want to put standard in, you want to do spike sample, you want to determine how accurate is your measurement, how accurate is your method. So all of these are required so that we know what we are getting is indeed accurate and precise. Yeah. So that is why QC and QA are so important here. And yeah, read yourself. Frankly speaking, I I was right not to extend this to pre-treatment and extraction technique, but I think next time when I have a chance, if I explain further on the soil sampling techniques, then possibly I will cover back yeah, pre-treatment and extraction. Actually, pre-treatment and extraction involves a lot in soil and also water sampling. So by that time, if I have enough time, then I explain to you But for today, I think that is all from me. That is all from me.